All right, so welcome once again to our channel. Welcome once again to our channel. Please kindly subscribe to this channel so that we can bring more content your way, and so that you can also be the first person to see our content once we upload it. So kindly click the red subscribe button at the down corner so that we can promote our content and we can bring more content your way. Now, in this video, I will teach on Poisson probability distributions. So in the earlier video, in the earlier two videos, I explained what probability distributions are. That was the first video. And the second video, I talked about the binomial distribution. In this video, I'll explain the Poisson distribution. The Poisson distribution. Now, one of the striking features of the Poisson distribution is that it is used as a limiting form of the binomial distribution. So here, one of the key features you must pay attention to for you to be able to distinguish between binomial and Poisson is that Poisson is usually applied where the probability of success is very small and the probability of failure is very high. Okay, where the probability of success is very small and the probability of failure is very high. That is when we employ the Poisson. So it is in simple words, it is used to describe the distribution of rare events in a large population. Okay, so here the probability of success must be very small for you to use the Poisson. The probability of errors must be very small, and then the number of trials must be very large. Okay, so the probability of success is very small, probability of failure very high, and the number of trials to very high. So this is the key to using Poisson distributions. So here, when the number of trials is very high, approximately when n is equal to greater than or equal to 100, when the probability of success is very small, approximately when p is less than 0.05, okay, when we have a finite mean, when the variable is descriptive, and when the trials are independent. For me, the basic striking feature is that find out whether p is less than or equal to 0.5. That is the basic feature that distinguishes binomial from Poisson. Now, the formula for Poisson is quite simple. So probability of x is equal to x, where we have e raised to the power minus lambda multiplied by lambda raised to the power x over x factorial. Okay, so in essence, the lambda is just the mean or the average or the expected value. So the mean or average or expected value. Okay, that is the lambda. Okay, all right. Then the x, of course, is the number of successes. Okay, then the e is simply the base of a natural log, which we can find on our calculator. Now, before we move on, let's know some basic terms as well. Now, let's note that for discrete probability distributions, whether binomial or Poisson, let's note that one of the key features is that here, approximately, you must know that if you multiply the number of successes by the probability of success, we should get the mean or the expected value. Okay, the expected value. So sometimes they may give you the number of successes, the number of trials, and give you the probability of success. Then when you multiply this, you now get the expected value or the lambda. So NP is simply the lambda. The N times the P is simply the lambda, okay, or the mean. Let's look at this scenario. Suppose that the average number of cars on the highway, suppose that the average number of car accidents on a highway is 4. So here, the word average number simply means that we are talking about the mean or the lambda. So lambda is 4. What is the probability that the probability of no car accident in one day? Okay, in one day, probability of no car. So it says that the average number of car accidents on a highway is 4. In one day is 4. What's the probability of no car accident in one day? So here we are looking at the number of successes is 0. Okay, because we're looking at no car accident. If you have one car accident, the number of success would have been 1, and x will be equal to 1. So from our formula, we have e raised to the power minus lambda, okay, multiplying lambda raised to the power x, all divided by x factorial. So here we have e raised to the power, the average or the lambda is 4, so we have minus 4. Then the lambda is 4, so 4 raised to the power, the x here is 0, so we have 0 all over x factorial, which is 0 factorial. And that is how we simply find it. Then the final answer will be 0.0183. 0.0183. Okay. All right. Now, the second question here says that suppose the average number of calls made by 104 students in 1 minute is 2. What is the probability of 10 calls in 5 minutes? So first of all, we must find our average or our lambda. And we are looking for the average number of calls in 5 minutes. So for 2 minutes, the average number of calls in 1 minute, is 2. So it means that the average number of calls in 5 minutes will be 10. Okay, because if 1 minute is to 2, 5 minutes is to 10. So the average number of calls will be 10. So what's the probability of 10 calls in 5 minutes? Okay, they are looking for probability of 10 calls in 5 minutes. So 10 calls here means that the probability of successes will be x is equal to 10. Please, it's just a mere coincidence that this is 10 and that is 10. Okay, so let's not confuse ourselves. So plugging them into our formula, e raised to the power minus lambda will be e raised to the power minus 10. Then lambda raised to the power x. So lambda raised to the power, the x is also 10. So 10 raised to the power 10 all over x factorial, which is all over 10 factorial. Then this will be the final answer. Okay. So this brings us the end of Poisson probability distributions. Poisson probability distribution. So in the next video, I'll come your way with normal probability distributions, but please, I'll urge all of us that let's kindly subscribe to the YouTube channel so that you'll be the first to see our content once we upload it. So kindly subscribe to the YouTube channel, share on several pages or platform you are on, and then we can bring your way more content. So see you soon in the normal probability distribution.